conjugated pi system, what we're saying is the alternating single and double bond. So all the carbon atoms in my 1,3-butyl diene are sp2 hybridized. It's alternating double and single bond, and it is a conjugated diene. In our last lecture, we spent some time looking at the pi correlation diagram of the 1,3-butyl diene. And one of the interesting take-home message we get is we look at these pi MOs, right? So pi 1 is the lowest lying molecular orbital. All the p electrons, all my pi electrons are delocalized. And this is the result why my C2C3 single bond is stronger than your normal single bond. That's not in a conjugated diene. Moreover, we also went over some of the nomenclatures in how to read the molecular orbital diagrams, like the HOMO by its namesake, highest occupied molecular orbital, and then LUMO is the lowest unoccupied molecular orbital. And when creating this pi MO, you first work out how many nodes are there, and the more nodes you have, the higher the energy that MO will be. So with that in hand, we are now ready to move on to look at some of the properties of our conjugated diene. Right, so this is what we're talking about. The single bond between the C2 and C3 carbon in my conjugated diene has a much shorter bond length comparing to a normal single bond like in ethane or in butane. And this is indicating that C2-C3 carbon-carbon bond is a stronger bond comparing to a pure single bond. And by analyzing the MO diagram of the 1,3-butyl diene, we figured, okay, so the reason behind this bond being stronger is because it has some pi character in that lowest lying molecular orbital. So with that in hand, we can look at some of their chemical properties of the conjugated diene. So for example, if we're looking at the heat of hydrogenation, so that means we react a conjugated diene with two molecules of hydrogen. So we're adding the hydrogen onto that unsaturated carbon-carbon bond to make it an all-saturated compound. And the heat of hydrogenation for my conjugated diene is about negative 57.1 kilocalorie per mole. So the process releases 57.1 kilocalorie per mole of heat. In comparison, if we're looking at the non-conjugated diene, so in this case, these two double bonds are being separated by a sp3 carbon. So by definition, that's a non-conjugated diene. And the heat of hydrogenation of the non-conjugated diene is greater, which is like negative 60.8 kilocalorie per mole. Or what we have is less energy is released from hydrogenation of conjugated diene. So if you think about it, they all end up with the same reference point, and the conjugated diene is releasing less heat coming from the hydrogenation, means my conjugated dienes are more stable compared to the non-conjugated dienes. And the reason why conjugated diene is more stable is because of that stronger C2-C3 bond. And we went from bottom up, right? We were looking at the MO diagram, and we rationalized why the C2-C3 has a stronger bond, and then we end up to the experimental observation, hey, conjugated dienes are more stable. All right. One last thing of the conjugated dienes I want to mention is that there exist two conformations of 1,3-butyl diene, depending on their relative position of your double bonds. So the most stable conformation for your 1,3-butyl diene is the S-trans conformation. So when we say S-trans, what we're saying is this carbon here, well, these two double bonds here are trans to each other in this zigzag kind of formula. Alternatively, if we're rotating around that C2-C3 single bond, we can get the S-cis conformation. So the energy difference between S-trans and S-cis is about 2.8 kilocalorie per mole. So what we're doing here is rotation of the middle bond. And the reason my cis is less stable is because the steric repulsion between the two hydrogen groups that are pointing towards each other. The barrier here is not extraordinary. It's higher than the barrier to rotate that single bond in the ethene, but it's still like possible at room temperature. So in 14D, you'll occasionally see reactions that are only possible with S-cis conformation of the diene. And the reason it can undergo this isomerization is because its rotational barrier is not too extraordinary if we only have hydrogen. But at the same time, you can also easily picture, right, if I replace that hydrogen with a very sterically bulky group, like a tributyl group, then this rotation will become less likely. But that's a little bit of addition that you'll see in 14D. All right, so that's the leftover topics of the 1,3 butadiene. And let's do a problem together and see how we're going to use our knowledge to solve chemical problems. So, again, this is 14C, so I don't expect you to know or to remember any reaction. I'll always give you a simple reaction, and you want to use your knowledge, your understanding of the reactive intermediate of these conjugated systems to try to rationalize the reaction outcome. So the problem we have here is, say, here's a reaction called electrophilic attack on a conjugated diene. And what tells you is this forms two different products via a carbocation intermediate. So can you predict the product given the following reaction mechanism? So I'm telling you this reaction forms a carbocation intermediate. Once you have that carbocation intermediate, that will react with a nucleophile, in this case bromine minus. And what kind of product will you predict? So what this question is actually asking about is what are the two stable carbocation intermediate you would expect? All right, so let's just look at it and see how to approach this problem. Here we're giving a conjugated diene, and we're giving the arrow pushing, right? So the double bond is attacking the proton here. If you think about it, there are two possible ways this proton can be located. One of them is more stable comparing to the other. So one of the way it can attack is on this internal carbon. And that remains the same. And we end up with a carbocation like that. Alternatively, it can also attack on this terminal carbon. And we end up with a proton in that middle position. Right, so it looks like an unfair question that shouldn't exist in 14C, but in reality, we're talking about the stability of that carbocation intermediate. And now we look at these two structures, and the answer becomes quite obvious. This is a 1,3 butadiene reaction of proton, and among these two cation intermediates, this one is more stable because it is an allylic cation. All right, and this allylic cation have two different forms. Remember when we were saying allylic compounds has the positive charge centralized on the terminal of my allylic group. So in this example, what is my allylic group? So here, that's my carbon 1, carbon 2, carbon 3. So these three red dots consist of my allylic carbon. So that means we have a resonance structure of this carbocation that looks like this. All right. And in this case, both of these two resonance structures are relatively stable allylic carbocation intermediate that can lead to successful formation of the product. We know the nucleophile is of a bromine, so naturally we can predict two different products from these two allylic cation intermediates. Well, one of them is you have the bromine around, comes in, reacts with that carbocation, and we end up with that product. And at the same time, You can also have the bromine comes in and react with that carbocation at the left terminal. And that's the product we're getting. Just as an add-on of nomenclature of these reactions, so if you think about it, here is the reaction happening on the 1,2 position. So this is called a 1,2 addition. And the bottom one is called a 1,4 addition. And the name comes from, like, if you do like 1, 2, 3, 4, 1, 2, 3, 4, and that's where the name comes from. You'll see more about 1,2 versus 1,4 addition in 14D, but this is just a heads up. By understanding allylic cation and the stability of the allylic cation, you can already do something in predicting the reaction outcome, even if we haven't learned this reaction yet. All right, so by understanding the mechanism, you can do a lot. Like, you don't have to remember everything in organic chemistry. All right, so that's all I have on topics of conjugated diene. And let's see if we have questions before we move on. I'll pause a little bit for you to think about it. Yeah. Right. So the quick answer is yes. If instead of a diene, you can have a triene or even a tetrazine, but that's a little bit above the 14C series. But we will see benzene in our next lecture, which has 3 alternating single and double bonds in a cyclic structure. All right, so that's the diene part. So this part is a little bit more on the theory, but we're trying to approach it from the theory point of view. So you're getting understanding of the structure, of the fundamental structure of your reactive intermediate, and we can potentially use that information to understand some of the reaction outcome for organic reactions. All right, so now it's time to move on to our next topic, which is a little bit of spectroscopy. So this part will be based on our understanding of the diene, and then we'll start to see some of the tools organic chemists use in order to depict those like electronic states, right? Those energies or those information about a microscopic electronic structure. So this is a little bit of the review, or I don't know if it's a review, so I just want to go over it with you. So here are a basic setup of atomic absorption spectroscopy. So what does it mean? Is you start from some kind of light source. You have a sample in between that can absorb energy from that light source. And after that, light passes through a slit and go degenerate into different color, you end up with a spectrum. So in the typical atomic absorption spectroscopy, you end up with a spectrum which is like dark lines on bright backgrounds. So the question here is, what is actually happening in that sample? What is taking place? What does these lines mean? So the easiest picture you can imagine about is, remember when we were doing electron configuration, you write your atomic energy level as like 1s, 2s, 2p, 3s, etc., etc. So all those energy levels, you can quantize it down into these different energy levels. And the result here is when your atom absorbs energy of a certain frequency, that wavelength or that frequency of light will disappear on your absorbing spectrum, which ends up to be a dark line. Right, so if we put it on the energy level diagram picture, what we have is we start at the initial position and your sample absorbs light. And when it's absorbing light, depending on the frequency of the light, your electron can be popped into different energy states. Right, so it gives you different H mu1 or H mu2 or h mu 3. So depending on the frequency of the light that's being absorbed, which is information you can read by reading the absorption spectrum, you can get information about energy levels in your atom. So this should be a quick review on the atomic spectroscopy. And then the idea is actually the same for organic molecules. So now let's look at our one-distributed dying, because we were just finished talking about this pi correlation diagram. So the idea here is the same. As we were doing the pi correlation of one-distributed dying, what we find out is that the energy level in our organic molecules are also quantized, right? So these are the higher lying pi molecular orbitals that can be potentially excited if we're just using a relatively low energy beam of laser, like UV or visible light. So that's the pi correlation diagram we created for one-distributed dying. You have pi 1, pi 2, pi 3, and pi 4. Your pi 2 is the HOMO, your pi 3 is the LUMO, etc., etc. So what is happening if we put my one-distributed dying and I shine light on my one-distributed dying? What is going to happen? So what we have in mind is, say we have a molecule that is at its ground state. It can potentially absorb energy from the photon. So this one will do a quick review. So energy of the photon equals to Planck constant h times the frequency of the light. All right. And again, the reason behind this equation, E photon equals to h mu, is your light is actually consists of small, like photon. Each photon has a small packet of energy. Depending on what the frequency of your light is, each of those small photons will have different kind of energy levels. Or on the other hand, we can also rewrite this expression into hc over lambda. So c here is the speed of light, and lambda here is the wavelength. Right. And the reason we can rewrite it is the speed of light equals to wavelength times frequency. And that's the inherent property of any electromagnetic wave. So what is happening is when E photon of energy is being absorbed by your molecule, essentially what happens is one of your electron, will get promoted into a higher energy state. Or in my excited state, what we expect, the bottom one stays the same, and then one of it will get promoted onto a higher energy state. And by measuring this E photon, which equal to h mu, we can get an idea about what's the energy difference between my pi 2 and pi 3 in this case. And this gap here is my HOMO-LUMO gap, which equals to E photon. All right, so that's one of the fundamental idea of my UV-Vis absorption spectroscopy. You have a sample. Your sample will only absorb light of certain frequency, right? So the lowest energy gap you can get is the energy gap between your HOMO and your LUMO, and in this case, that's equals to your photon of energy that has the smallest frequency or largest wavelength, if you may. Any questions on the basic of spectroscopy? We'll use this kind of idea in our future spectroscopy topic. So the idea is always the same. It's you have a sample, you have a molecule, and you somehow perturb that molecule with either a magnetic field or a light, and you observe how your molecules react with that perturbation of your light or magnetic field. And that is the information your molecule is trying to tell you, like what are the properties you can get of that sample. So spectroscopy is our eye to the microscopic world. So with that in hand, we can look at the UV-Vis absorption spectroscopy. And here's a typical experimental setup. You'll probably use it in your biochemistry lab or even biology lab, and also the coming 14C-L lab as well. The idea is the same. On the left-hand side, we have the light source. I say H mu, but this one should be a general like white light source of, it's not of any specific wavelength or frequency. We use the light to shine two different cells. One is my sample cell, and one is my reference cell. So the reason here is when we're looking at spectroscopy of organic molecule, you want to exclude the effect of solvents. But whatever solvent we are using, I don't want to see the effect of my solvent. I just want to focus on my sample. So in my sample cell, we have solvent plus sample, and then in our reference cell, we have solvent only. It's going to reach the detector with certain frequency, and therefore comparing the difference between these two intensity, we get an idea about how much light is being absorbed by my sample comparing to how much light is being absorbed by the solvent only. And then what we're going to do is let's look at a sample spectrum together and try to see how to get information, how to get like chemically meaningful information by just looking at the sample spectrum. So here's the spectrum we have in mind. On the y-axis, we have the absorbance. So that's actually defined by the logarithm of your intensity difference comparing to the two source, the sample versus the solution. And on the x-axis, we have the wavelength. So the wavelength tells you at which position your sample is being absorbed most strongly. Your sample is absorbing light most strongly. So we can get two different kinds of information by looking at the x and y axis of your spectrum. So on the x-axis, that's giving us information about the homolumo gap, and we'll see how to do that. And on the y-axis, it's giving us information about the concentration of the solution using Beer's law. We'll also see an example like that. So I'm just going to keep this spectrum here for your reference while we're working on it. Let's see. I'm just going to leave it there for your reference. First thing first, lambda max. So lambda max, what does that mean? Is if we're having wavelengths of like from 200 nanometer all the way to 400 nanometer, it tells me, hey, your sample absorbs most strongly around 280 nanometer, or in this case, 217 nanometer, I'm sorry. And as we remember, the smallest possible gap we can get in this diagram is the homolumo gap. And everything else will require a much larger wavelength. It's not even in my UV region. So what that tells us is by looking at the lambda max, we can get information about the delta E between your pi2 and pi3 molecular orbital. And this delta E equals to H mu. Again, H is my Planck constant. Mu is the frequency of the light. But in this case, we only have the wavelength, but you can easily transfer that into Hc over lambda. All right, so let's just work on that together and see what is the homolumo gap in my 1,3 butadiene. So one of the possible questions would be, hey, this is a UV spectrum of 1,3 butadiene. Can you calculate the homolumo gap and express your answer in kilcal per mole? And note I might also ask you to sketch what does the homolumo gap looks like, just as a relevant point. So going back to our analysis, we know that delta E equals to E photon, which equals to H mu or Hc times lambda. So here, h is Planck constant, c is speed of light, mu is frequency, and lambda is the wavelength of the light you're using. And then we can plug in numbers to do that calculation. So h is 6.626 times 10 to the negative 34 joule second times my speed of light, 2.998 times 10 to the 8th meter per second. And my lambda, obviously, that's 217 nanometer. But I want to translate that unit into meter, so times 10 to the negative 9 meter per nanometer. And note that the question asks you to express your answer in kilocal per mole. So far what we're doing here is just calculating the delta E for one molecule of butadiene. And what the question is asking for is one more of molecule of butadiene. So I need to times the Avogadro number. So 6.022 times 10 to the 23 more. All right. And let's see if my unit cancel out correctly. Well, S cancel out, that cancel out, meter cancel out. So the unit of my calculation right now should be in joule per mole, and we need to translate that into kilocal later on. But let's just plug in the numbers together. So 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8th times the Avogadro number times 10 to the 23 divided by 217 times 10 to the negative 9. And we end up with something like 551 kilojoule per mole. And you can translate that into kilocal per mole, which is about 132 kilocal per mole. Right, so leave aside all the calculation. The information we're getting by looking at the x-axis of your UV-Vis absorption spectrum is at which wavelengths my molecule absorbs light most strongly. And by looking at the wavelengths it's absorbing more strongly, you can get information about its electronic structure. So in this case, it's a HOMO-LUMO gap between my HOMO, or highest occupied molecular orbital, and LUMO, which is my lowest unoccupied molecular orbital. All right? And then that's the x-axis. Now we can switch gear to look at the y-axis of my spectrum. And what we can get here, to analyze the y-axis, the law we're using is Beer's law. You probably already see that in previous classes or AP chemistry. In Beer's law, what we have here is absorbance, which is what we're measuring here. That's getting by taking the logarithm of the intensity difference between your two cells. And this absorbance will equal to epsilon, which is the molar absorption coefficient that has a unit of liter per mole per centimeter, the concentration of the sample, and also the path length, or the length of the unit cell you're using. Or if it's in a biochemistry lab, as you remember, people call it a cuvette. So the length of the cuvette is important in this part as well. So by looking at this, obviously you can use it in two different ways, right? One way is you know the molar absorption coefficient, you know the path length, and you're trying to derive the concentration of the sample. Or the other way is in case you do not know the molar absorption, you can take multiple samples with different concentration to identify the molar absorption coefficient, and then use those numbers to determine the concentration of your sample molecule, of an unknown sample molecule. Nevertheless, so those are the techniques you will need in the lab course, and also you'll see that in the discussion session later this week. But let's just do an example question together. So let's just given the molar absorption coefficient here to be 21,000. The length of the cuvette is 1 centimeter, and calculate the concentration of your butadiene solution, and express your answer in mole per liter. So in this case, the equation we're using is Beer's law. That's epsilon Cl. Or in the other way, we know that C concentration equals to A divided by epsilon L. So it is a little bit unfortunate. The speed of light and your concentration both have abbreviation of C, but they are just completely different things. I don't mix them up. And we have C equals to, well, A equals to 0.82 divided by epsilon, which is 21000 liter per mole per centimeter times 1 centimeter. And this calculation is relatively straightforward, just like 0.82 divided by 21000. That's about 3.9 times 10 to the negative 5 mole per liter. All right? So going back to our original spectrum, what does our UV visible absorption spectrum give us? So it can give us two different pieces of information depending on what you're asking for. So looking at the x-axis of the peak of your absorption spectrum, it gives you information about where the absorption is stronger, or in general, it gives you the homo-lumo gap. And if we're focusing on the y-axis, the absorption picture, what we have is we have the Beer's law, and it gives you information about concentration. All right. All right, let's see if we have any questions before we move on. Nope. Again, every time there's no question, I'm like super panicked. But I guess it's okay. We can move on. The last little bit of the topic we want to talk about is how does electron delocalization leads to different kind of electronic spectrum. So one of the things we just covered, right? So the delta E, or where my absorption peaks, gives me information about the homo-lumo gap of my sample. So in general, in organic chemistry, this is not quantitative, but you can use it as a qualitative rule, is when you have more conjugated pi system, which means you have more extended conjugation, like say a triene, or you have multiple aromatic groups, which we will see in our next lecture. So the more conjugated pi systems will tend to have smaller homo-lumo gap, or in general, they will have larger lambda max. I'll pause a little bit here to see if it makes sense to you. Smaller homo-lumo gap means this difference between the homo and lumo becomes smaller. So that tells me, this gives me smaller delta E, and we know that delta E equals to h mu, but mu equals to c divided by lambda. Right, so smaller delta E tells you it's a smaller frequency and consequently larger wavelength. So that's the logic behind that statement. So if we take the example of ethene, which is just a single double bond, the homo-lumo gap of ethene is about 171 nanometer. Where for the 1,3 butadiene, we just see the absorption wavelength peaks at 217 nanometer. All right. And when we move on to organic molecules with even more extended conjugated systems, what we will end up, we're getting very colorful molecules with, well, people use it as organic dye. So you'll see that in your discussion worksheet in why organic dyes have so colorful have so much colorful numbers. So organic dyes, they're typically very highly conjugated molecules. And what happens is when a molecule absorbs certain wavelengths in your visible region, what we will see as human beings when we observe that absorption of the light, we'll see its complementary color. So let's say a hypothetical molecule have like wavelengths absorption peaks at around 600 nanometer. What kind of molecule we will observe? So it's going to be a purple color of that molecule. All right. See if we have questions before we move on. No, not really? All right. Yeah, I intentionally make this lecture a little bit shorter because we are trying to catch up in our lecture, but I think I made it a bit too short. But it's okay. I'll give you a heads on when we're talking about aromatic compounds. So I'm just going to quickly write here. I don't have my lecture notes ready yet. So aromatic compound, when we're talking about it, what we're having is a cyclic molecule that is planar. So I'll use our benzene as a example here. It's a cyclic molecule. It has alternating double bonds or conjugated double bond in your system. And the interesting thing about benzene is if you look at its molecular orbital, we have 6 electrons here in benzene, 6 pi electrons, if you may. And if we look at the molecular orbital of benzene, you'll see a relatively interesting behavior. We'll go over everything like more systematically in our next lecture. Just I have 10 minutes left, I thought I should give you a head start. When we look at the molecular orbital of benzene, like if we put it on the plane diagram, and again, we're doing the same thing we're doing for our butadiene, right? All my carbon here are sp2 hybridized. So we have a total of 6 p atomic orbitals contribute to your pi correlation diagram. Again, we start from 0 node, and we want to go up to see what are the molecular orbitals look like. So one interesting thing about benzene is because of its cyclic structure, cyclic planar structure, you have 2 different ways to place that node. And the result is you end up with 2 degenerated pi molecular orbitals. So degenerated just means they have the same energy, same number of nodes. So what that means is when we're drawing that one node, you have 2 different ways to draw it. You can either draw it through bonds, or we can draw it through atoms. And when we go to the 2 nodes, likewise, you can draw it through bonds, or you can draw it through atoms. And when we go to the 3 nodes, and then we actually have only one possibility. You can't draw it through atoms, otherwise you don't have any MOs left for the 3 nodes. So what does these MO look like? So if we think about it, that's the way we put it. In the lowest energy one, they're all delocalized over the entire ring. And then in the 1 node situation, if it's through atom, it looks like that. If it's through bond, well, it has a different shape. All right, so whenever you see a node plane, you flip the sign of your atomic orbital. So that's a most important take-home message when you're creating these molecular orbitals from atomic orbitals. And likewise, if we're doing that for my 2-node, we flip, and then we flip back. So whenever you see a node plan, you flip that node. And something like this. And when we're going up to the highest energy MO, we're flipping at every node plane. Correct? So then it comes to the question is, well, what is my HOMO, what is my LUMO, and why is benzene a relatively inert species? And what do you mean when we say aromaticity? Aromaticity is just a term when we're saying, hey, your electrons are so delocalized, it's so stabilized, it's actually a unique type of molecule that are stable. So in this case, what we have is my pi 1. That's my pi 1, pi 2, pi 3, and pi 4. We have a total of 6 electrons. We put it in. And these are all in my low energy molecular orbital with X maximum, just 1 node. And they're relatively stable. So this is also why when we're talking about benzene or aromatic compounds, people also draw it as a fully delocalized picture with just a circle in the middle. So both ways are correct. You have the Kukila way of drawing it, where you have the 2 resonance structure, or people just draw it with a circle in the middle. That is also all right. And now let's just take a step back, right, and think about now we have benzene. What if we have a cyclobutadiene with just 4 pi electrons, and why that is not stable? So this one is benzene. And now let's think about cyclobutadiene, or a molecule that's having the 2 diene, and they assume it's a planar geometry with 4 carbon atoms that are sp hybridized. So the way to put it is, let's look at this picture and how to put my atomic orbitals together. And in the 0 node, this is all right. We don't have any node. What comes to the problem is when we're having the 1 node scenario. Again, you have 2 different ways. You can draw the node plan, whether it's through atom or through bonds. And then the 2 nodes will be both through bond. So the result here, if we draw it out, are structures like this. And when you're putting electrons into these molecular orbitals, now we're having a problem in the butadiene scenario. We have a total of 4 electrons. So when they are entering the degenerated pi 2 molecular orbital, they will enter it like 1 at a time, right? So that's the Hund's rule we talk about to avoid electron pairing energy. So we end up with 2 singly occupied molecular orbital, making it super reactive or unstable with the light. So you all know Huckel's rule. So here comes to one of the example or applications of the Huckel's rule. So in the benzene, we have 4n plus 2 pi electrons. And all my low energy molecular orbitals are doubly occupied. Well, in comparison, when we're looking at the butadiene, cyclobutadiene, these 2 molecular orbitals are degenerated and singly occupied. And these are anti-aromatic with 4 pi electrons. We'll go over them more systematically, but I just thought to give you a head start on these MOs. All right, I'll see you on Wednesday. Yes. 1 second, let me just pull my next lecture up. Okay. All right, here we go.